Today, we're going to pull back the curtain on a process that's, well, absolutely fundamental to the quality of countless products you use every single day. It's called sieve analysis. Now, it might sound a little old school, but trust me, this technique is a powerhouse for understanding what materials are really made of. So let's dive in.
All right, let's start with a bit of a riddle. What could your morning coffee, the cement in a skyscraper, and the powdered sugar on a donut possibly have in common? I mean, really think about it. The connection is something you can't even see, but it's absolutely critical for all of them.
And the answer is particle size. Yep, the quality of all these things and so many others comes down to how big or small their tiny little particles are. This one single property influences everything, from how your coffee tastes, to how strong a building is, to how a chemical reacts, and even how conductive a material might be. It is the secret ingredient, the hidden variable that makes sure a product does exactly what it's supposed to do.
So, how in the world do we measure this invisible but totally vital property? Well, that's where sieve analysis comes into play. We're about to follow the journey of one single sample to see exactly how this whole thing works, right from the very beginning.
First things first, before you do anything else, the absolute most important step is getting a good sample. It has to be, and this is the key word, representative. That just means that the little bit you test has to have the exact same mix of particle sizes as the entire batch, whether that's a giant silo of wheat or a truck full of sand. If your sample isn't representative, well, the entire test is basically worthless.
Now for the main tool of the trade, the test sieve. And let me be clear, this is not your kitchen strainer. A test sieve is a serious piece of precision engineering. Each one has a wire mesh with incredibly uniform openings of a very specific size. And they're all made to follow super strict international standards. That's what makes the results reliable and repeatable anywhere on Earth.
Okay, we've got our representative sample, we've got our stack of precision sieves all ready to go. Now it's time for the action. This is the part where we physically sort the particles. But you can't just shake it any old way. The way you shake it is actually a scientific decision.
You've basically got two main methods. On one hand, there's throw-action sieving. This is a three-dimensional movement, up, down, and around, that literally tosses the particles in the air so they have the best possible chance of finding an opening. It's great for most grainy materials. But then you have horizontal sieving. This is a much gentler motion, just flat circles. It's perfect for things that are long or fibrous, because it keeps those needle-shaped particles from getting stuck vertically and clogging up the mesh.
Another big choice you gotta make is the environment. Most of the time, you'll do this dry. It's simple, it's straightforward. But sometimes, especially with super fine powders, the particles they get sticky. They clump together. For that, you use wet sieving. A special nozzle sprays water to help break up those clumps and wash the fine particles through the mesh, which gives you a way more accurate result.
So how long do you shake it, and how hard? You don't just guess, it's a really methodical process. First, you play around with the shaking intensity. That's called the amplitude, to find the sweet spot for your material. Once you lock that in, you test different sieving times. You know the test is officially done when shaking it for one more minute changes the weight on any given sieve by less than 0.1%. That's how you know you've hit a stable, true result.
Okay, the shaking is over, the dust has literally settled. What we have now is a stack of sieves, each one holding a different size group of particles. Now comes the moment of truth, weighing each fraction and turning all those raw numbers into a story about our material.
But wait, before we even look at the results, there's one last crucial quality check. You have to weigh everything you collected on all the sieves, add it all up, and compare that final number to the weight you started with. That difference is called sieving loss, and the rules are strict. If you've lost more than 1% of your sample, maybe it floated away as dust, the test is a bust. You have to start all over again. So, assuming our test passed the 1% rule, this is what we get. The middle column shows the percentage of our sample that was caught on each sieve. The column on the right is just a running total. But let's be real, a table of numbers doesn't really pop, does it? It's hard to get a feel for the material just by looking at this.
But this is so much better. We can take that data and turn it into a histogram, and suddenly you're looking at the material's unique fingerprint. It just jumps out at you. That tallest bar tells us that the single largest group of particles, a full 35% of our sample, is between 0.125 and 0.250 millimeters. It's a powerful story, all in one quick glance.
Remember that cumulative data, the running total? That gives us another incredibly powerful way to look at things. From that data, we can make a really simple, really strong statement.
For example, we know for a fact that 67% of this entire sample is made of particles smaller than 1/4 of a millimeter. You can imagine how useful that is for quality control.
But here's the really cool part. Out of all that shaking, weighing, and calculating, we can often distill the whole story down to a single, incredibly powerful number. For our sample, that number is 0.189 millimeters. So what does that even mean?
This is called the X50 value. It's the median. It's the perfect halfway point. It means exactly 50% of the particles in the sample are smaller than this size, and the other 50% are larger. And this is why it's so important. For a cement maker, if this number is off, the concrete could be weak. For a coffee company, it could mean the difference between a perfect brew and a bitter one. This one number is often the critical checkpoint.
So you might be thinking, with all the high-tech lasers and imaging systems we have today, why on earth does this seemingly simple method of just shaking stuff through screens still dominate so many industries?
The answer is pretty simple, because it just works. Sieve analysis is proven, it's incredibly reliable, and it's pretty inexpensive. It gives you quick, accurate results that people understand and trust all over the globe. It's a cornerstone of quality control everywhere, from drug manufacturing to mining, because of its straightforward, rock-solid reliability.
So the next time you pour that perfect cup of coffee, or you're walking on a solid sidewalk, just remember the unseen science that made it all possible. A simple, controlled shake revealing a material's deepest secrets. It kind of makes you wonder, doesn't it? What other hidden properties are shaping the quality of the world all around you?